Hello and welcome to this video on how we can solve non-homogeneous second-order differential equations. In one of our previous videos, we introduced the topic of second-order differential equations, and we saw several examples of what are known as homogeneous equations. These equations are known as homogeneous because we can arrange them in this form here, where we have a second differential term of y with respect to x, a first differential of y with respect to x, and a y term, and arranged like this is equal to 0. This is what's known as a homogeneous second order differential equation. And if that's not the case, if we arrange it in that form but the equation is equal to a non-zero value, it could be a constant, we'll call it k, or it could be the case, and this is what we'll look at mostly in this video today, equal to a function of x, we'll call that Rx. These are examples of non-homogeneous second-order differential equations. So the good news is that when we solve non-homogeneous differential equations like these, the method is going to be very similar to when we solved homogeneous equations as in one of our previous videos. If you haven't already watched our first video on homogeneous second-order differential equations, it's worth going back and watching that first before we continue with this video, because we're going to use a lot of the same principles here as well. We're going to follow 3 steps to solve a non-homogeneous differential equation. The first step is we're going to solve the corresponding homogeneous equation, and we're going to call this the complementary equation. What we're essentially doing here is pretending that the equation is homogeneous. We're going to replace the term on the right hand side here with 0, and we're just going to solve it as if it was homogeneous anyway. Secondly, we're going to guess the form of the particular solution, and we'll talk a bit more about that in just a moment. And then finally, step 3, we're going to substitute some values and solve to find the general solution for our non-homogeneous equation. So the first point to make is that we are already familiar with step 1 if you've been following our previous videos, because that's to solve a homogeneous equation like examples we've looked at already. The additional steps involve a little bit of guesswork and rearrangement and solving, so there's not much more to do, but there is a little bit more work compared to a normal homogeneous equation. And looking at step 2 here, we see that we're going to be required to make a guess of some description at the form that a particular solution will take. The form of that guess is dependent on the form of the right-hand side of the equation. And in this case, we're going to look at a range of different examples where the right-hand side takes a function of x. There's many different forms that the function of x, Rx, could take. And we're not going to look at too many, but here's a few examples in this table of some different forms that the right-hand side Rx might take. And depending on which of the forms we see, we're going to make a corresponding guess as to the particular solution. So when we look at this table, there's a few things worth mentioning before we begin. First of all, what we know of Rx on the right-hand side of our equation doesn't necessarily inform us as to what we know about the guess on the right-hand side of this table here. I'll give an example. Let's suppose we have a non-homogeneous equation and the right-hand side is equal to 7. The guess is still going to be A. We don't know that A is necessarily equal to 7. We only know the form that that guess will take. Similarly, let's suppose that we have a right-hand side of our non-homogeneous equation that's equal to 3x plus 4. Again, our guess is going to take this form here, ax plus b, but capital A and capital B are unknown. You'll notice that we use small letters on the left-hand side, small a and small b, capital A, capital B on the right-hand side, because these aren't necessarily equal. All we can say is that we know that the guess is going to take this form. Another important thing to mention is that we must use the whole form that the guess takes on the right-hand side, even if our function is not complete on the left-hand side. Let's give an example. Let's suppose that the right-hand side of our equation, Rx, takes the form 4x squared, for instance. Well, here, because we don't have a x term and a constant term for the b coefficient and c coefficient here, we've just got an ax squared term here. That doesn't mean that we only use the capital AX squared from the right-hand side in the guess here. We have to use the whole guess in its full form if we're going to get correct results, because we don't necessarily know that capital B and capital C are 0 as well. So you'll notice that I've represented this with some asterisk symbols here because it's the case, for instance, in this last entry here, suppose we only have a cosine function with no sine present in our function for Rx. We still have to use the complete guess with a cosine and a sine in this full form here when we make our guess. So just to bear that in mind before we proceed. So we've mentioned 3 steps before, and I appreciate they probably don't make very much sense, but hopefully when we put them into practice with an example, it'll start to become a little bit clearer. Let's suppose that we are asked to find the solution for this non-homogeneous equation here. 3d squared y by dx squared plus 4dy by dx minus 4y equals 5x. So step 1 that we saw previously was to solve what we called the complementary equation. And in other words, the complementary equation is the equation if it was homogeneous or if it was equal to 0. And so in our case, it would look something like this. Now, to save a bit of work, I've purposely picked this particular equation because we've actually already solved this particular homogeneous equation back in our previous video when we introduced the topic of second-order differential equations. So if you're not sure about how to go about solving this particular homogeneous equation, it's worth going back to that previous video. But we found that y equals a e to the power 2/3 x plus b e to the power minus 2x. That was our general solution for y in terms of x for this particular equation. I want to do a couple of things at this point that just deviate slightly from the method that we've used in previous videos. First of all, rather than y, I'm going to give this the subscript yc, because if you remember, we called this the complementary equation that we were solving. And so yc just reminds us that this is only part of our solution, yc, the complementary solution to the complementary equation. The second thing I'm going to do is make a slight change to how we name these constants. If you have watched our previous videos, when we form the general solution of this type, we have these 2 unknown constants, which we've always called capital A and capital B. Now, if you remember our table of guesses that we're going to be involving soon, from the last section there, we had capital A's and capital B's in our guess formulations as well, and I don't want to get these 2 confused, and so I'm going to make a slight change here. I'm going to rewrite this equation, but rather than a and b, I'm going to call these unknown constants k1 and k2 instead, and that's just to avoid confusion at a later stage. So like I mentioned before, this is what we call our complementary solution. We've given it the term yc. So step 2 of the 3 steps that we looked at previously asked us to guess the form of the particular solution based on the form of Rx. Now, Rx being the right-hand side of our homogeneous equation as it's arranged, and in our case, Rx was equal to 5x. And referring back to our table, the closest form of Rx in our table is going to be Ax plus b, and so our guess must take the form of capital AX plus capital B. And remember, we'll have to use the whole form of that guess. And so this will take the form of what we call our particular solution. We're going to label that y with a subscript p there for particular. And that's a function of x. And for now, we say that yp is equal to ax plus b, capital AX plus capital B. And that's just for now. Remember, it's only a guess. This might change as we go through the next step as well. The last step, step 3, was for us to substitute our guess into our original equation. And we can do this by substituting for each of the y terms. The reason we do this is hopefully to allow us to find the unknown coefficients in our guess. At the minute, our guess has these capital A and capital B terms, and hopefully by doing a bit of substitution and solving, we can work out those unknown coefficients in our guess for the particular solution. So our initial equation involves y, but it also involves the first differential, dy by dx, and the second differential, d squared y by dx squared. And what we're going to do is we're going to substitute our particular solution, yp, into each of these y terms. But to do that, we're going to have to differentiate our particular solution as well. So we said that yp was equal to ax plus b. And that means that dyp by dx, the first differential, is going to be equal to a if we differentiate that expression. And differentiating again, d squared yp by dx squared is equal to 0. And so when we return to our original non-homogeneous equation and we substitute all of these in, we'll see something like this. And that simplifies a little bit, and we end up with 4a minus 4ax minus 4b is equal to 5x. So at this stage we have an equation in terms of a, b and x, but it's still not quite apparent what a and b are equal to. But what we can do is we can equate coefficients in order to find the values for a and b. Let's explain what we mean by that. So when we examine this equation above, we see that on the left-hand side of the equation, there's only one x term. It's this minus 4ax here. And on the right-hand side, we only have one x term as well. It's this 5x. And so it must be the case that 4ax is equal to 5x because we're accounting for all the x terms in this particular equation. And so we can say this minus 4ax equals 5x, and dividing both sides by x, minus 4a is equal to 5, and so a must be equal to minus 5 over 4. Now that we've accounted for all the x terms in the equation, we can also account for all the non-x terms. All the non-x terms, on the left-hand side we have 4a minus 4b equals 0, because there aren't any constants or non-x terms on the right hand side, and that means that 4a equals 4b, or a equals b, and so b must also be equal to minus 5 over 4 since b is equal to a. So we began with an initial guess for our particular solution. If you remember, we said that yp is equal to ax plus b. Well, now we know better. We know that a is minus 5 over 4 and b is minus 5 over 4. And so the final particular solution becomes this. We have yp is equal to minus 5 over 4x minus 5 over 4. Or we could express that as minus 5x plus 5 all over 4. The final step, which we haven't really mentioned, but it's very easy, the general solution to our whole non-homogeneous second order equation is something that takes the form of this. It's yx, our solution, is equal to yc of x, a function of x, plus yp of x. And yc of x, if you remember, was our complementary solution from step 1. And yp of x is our particular solution from the last step there. And so together they form our solution yx, which is our complete general solution for the non-homogeneous equation. So it's simply a case of adding both parts together. So in our case, we find that y equals k1 e to the 2/3 x plus k2 e to the minus 2x. That was our complementary solution. And then this minus 5x plus 5 over 4 on the end, which was our particular solution. And that's our complete solution for this example. Let's have a look at a second example. We're going to look at 3 examples altogether in this video. This time we have 3d squared y by dx squared plus 4dy by dx minus 4y equals 2e to the 2x. So we have an exponential function on our right hand side now in this particular example. You'll notice that the left hand side is actually exactly the same as example 1, and I'm doing this on purpose really. We know hopefully by this point how to solve homogeneous equations, and we're going to keep the left hand side the same just to keep this video as brief as possible. So step 1 is exactly the same as step 1 in the previous example. We're solving this complementary equation, the homogeneous equation, and we get the same complementary solution, which looks like this. Step 2, on the other hand, we have to refer back to that table of guesses and their forms. And in this case, we have Rx is equal to 2e to the 2x. And the corresponding entry in our table looks something like this. Notice that the lambda symbol is the same on both sides of the table. And so we're allowed to keep this number in our guess. So the form of our particular solution, the guess of the particular solution at least, is going to look like this. Capital A, e to the 2x. Again, we've preserved that lambda value because it's the same as for Rx as it is for the guess. For step 3, as in our previous example, we're going to substitute that particular solution as well as its first and second differentials into our original equation. And so we've said here that yp is equal to ae to the 2x, and differentiating that we have dyp by dx is equal to 2ae to the 2x, and d squared yp by dx squared, differentiating again, we have 4ae to the 2x. And so when we substitute these into the original equation, we're going to see something like this. We have these substitutions we've made for the y term, the first and second differentials. We can multiply those brackets out easily enough, and we can divide both sides by e to the 2x. We'll lose the e to the 2x terms on both sides of the equation. And so we're simply left with 16a equals 2. And that means that a is equal to 2 over 16 or 1 over 8. So now our particular solution takes the form of something like this. Rather than e to the 2x, we now have 1 over 8 e to the 2x, or it could be e to the 2x over 8. And so finally we stitch these two solutions together, the complementary solution and the particular solution, in the form of y. Our solution y is equal to yc plus yp. Well, we know the complementary solution remains the same, k1 e to the 2/3 x plus k2 e to the minus 2x, plus the complementary solution, which in this case is 1 over 8 e to the 2x, and that's our complete solution there. Here's the third and last example for this particular video, and we have the left hand side the same again. 3d squared y by dx squared plus 4dy by dx minus 4y, this time equal to a sine function, 7 sine 2x on the right hand side. And so step 1 again for simplicity remains exactly the same. We've found the complementary solution to still be the same, k1e to the 2/3 x plus k2e to the minus 2x. Step 2, on the other hand, we now have a value of Rx, or a function of Rx rather, taking the form of 7 sine 2x. And so our most appropriate guess from the table was this one here, a cos beta x plus b sine beta x. And again, remembering we have to use that whole guess, even though we don't have a cosine element to our initial function Rx, we still have to include it in our guess. And also notice that beta is present on both sides of our table, so we can carry that beta value over, as it were. Beta was 2, and so our initial guess for the particular solution takes this form. It's going to be a cos 2x plus b sine 2x. And step 3, we're going to substitute and solve. So again, we have our function of y, but we need it differentiated, both its first and second differentials. So yp, the particular solution, was a cos 2x plus b sine 2x. Differentiating that, so we've got dyp by dx is going to give us minus 2a sine 2x plus 2b cos 2x. So remember, cos differentiates to become minus sine, and sine differentiates to become cos. And we're differentiating again. We want the second differential as well. And differentiating again, we get minus 4a cos 2x minus 4b sine 2x. So when we substitute these into our original equation, we get something that's quite long. When we put all of those in, we get something that looks like this. And we can expand out those brackets a little bit, multiply out those brackets, and we express it like this. Minus 12a cos 2x minus 12b sine 2x minus 8a sine 2x plus 8b cos 2x minus 4a cos 2x minus 4b sine 2x is all equal to 7 sine 2x. Okay, so at this stage, let's equate coefficients like we did in a previous example, because we can see that on the right-hand side, there's only a sine term remaining. And that means that all of these cos terms must add up to 0, because we're not left with any cos term on the right-hand side. So what we can say is this. We can say that all of these cos terms, if we pick them out, minus 12a cos 2x plus 8b cos 2x minus 4a cos 2x must be equal to 0. And we can divide both sides by cos 2x, and we're simply left with minus 12a, plus 8b minus 4a is all equal to 0. And that means that we can simplify a little bit to minus 16a plus 8b is 0. Similarly, what we've left behind were the sine terms from the original equation there, and the total of all of the sine terms must add up to 7 sine 2x, because that's what we're left with on the right-hand side. And so we have minus 12b sine 2x minus a sine 2x minus 4b sine 2x equals 7 sine 2x. And again, we can divide both sides by sine 2x. We're left with minus 12b minus 8a minus 4b equals 7, which simplifies down to minus 8a minus 16b equals 7. So now we have two equations in terms of a and b. We have two simultaneous equations. We had minus 16a plus 8b equals 0, and now we've got minus 8a minus 16b equals 7. We'll not go into how to solve simultaneous equations, but using a method like elimination or substitution, we can find that a equals minus 7 over 40 and b equals minus 7 over 20. And so having solved these simultaneous equations, we can now express the particular solution, replacing the unknown constants capital A, capital B in our guess for the particular solution with these values that we found here. We have this yp is equal to minus 7 over 40 cos 2x minus 7 over 20 sine 2x. And again, remembering that simple little step at the end, our total sort of general solution for this equation, we stitch together the complementary solution and the particular solution. The complementary solution, same as before, we have that there, and we're adding what we've just found for the particular solution on the end. In this case, it will be minus 7 over 40 cos 2x minus 7 over 20 sine 2x to give the complete general solution for our third example. So I hope you found this video useful, where we've expanded on what we've covered previously when we first looked at homogeneous second order differential equations. and seeing how just with a little bit of extra work, a little bit of guesswork and rearrangement, we can solve for non-homogeneous differential equations as well.